Hello, my name is Abhishek and I'll be presenting our work on translation validation in presence of dynamic allocations and deallocations of local memory. This is a joint work with my advisor Professor Saurabh Bansal from IIT Delhi. Let's start with translation validation. A compiler takes a source program C, in this case a C source code, as input and produces a target assembly program A, in this case a 32-bit x86 assembly, as output. A translation validation tool, also known as a translation validator, takes both the C source code C and assembly A as input and produces a judgment on correct translation from C to A. The translation from C to A as performed by the compiler is correct if the translation validator asserts its correctness. Our setting is end-to-end translation validation problem where the two inputs are unoptimized IR obtained from a C program and 32-bit x86 assembly obtained from third-party compilation of the C program. We'll refer to the unoptimized IR as C and the assembly as A. In this setting, we focus on the case where C, the unoptimized IR, contains dynamic allocation and deallocation of local memory through constructs such as address taken local variables, fixed and variable length arrays, GCC alloca operator, and variadic functions. In this context, we define correct translation in terms of refinement of potentially non-deterministic behaviors. That is, in a correct translation, the observable behaviors of A is a subset of the observable behaviors of C. We motivate the problem through an example. Consider this read-in procedure. It defines an address taken local x whose address is taken through the address of operator $x as the second argument to variadic function scanf. The unoptimized IR for readint makes the allocation and deallocation of x explicit through the alloc and dealloc instructions. The alloc instruction allocates memory of requested size and returns the first address of the allocated region. Both the address and the memory contents of the allocated region are non-deterministic but subject to two well-formless constraints. First, the address interval of the allocated region does not overlap with currently allocated regions. Second, the start address is aligned by the required alignment for the allocated type, in this case int. The call to scanf procedure, which is external to current translation context, takes the allocated x as argument and may potentially observe it. For example, it may print x. The observable state of readint thus includes the program state visible to scanf. As scanf may observe the arguments and global memory state accessible to it, this program state constitutes observables for readint. Let us now look at the 32-bit x86 assembly compilation of readint. Here, the assembly stack is used for allocating x. By analyzing the assembly instructions, we can tell that the variable x resides in the stack space allocated by instruction A1. Recall that we need correspondence of observables for correct translation, and that includes the address of x, which in this case is some stack address. As stack is also used for spelling pseudo registers, identifying the required stack address is not straightforward. Another issue with the use of stack is that stack may potentially overflow. For example, it is possible for the 20-byte stack allocation in line A1 to overflow the stack into the program heap. Let's put our correct translation definition on a more concrete footing before discussing more nuances associated with assembly modeling. We define a trace as a sequence of observables, where observables include value of program variables or machine registers, memory contents, or events, including procedure call, procedure return, halt, or occurrence of error. We say that a procedure P executes with trace T sub P if procedure P, through a sequence of non-deterministic choices, may produce a trace of observables T sub P. For example, execution of readint may produce the following trace such that the relation holds. Note that the observables in this trace include a procedure call event for scanf, the arguments which are addresses of the format string and variable x, and the memory visible to scanf, which is the heap and memory region of variable x. We define correct translation through a refinement definition. A defines C, or C is defined by A If and only if, whenever A executes with trace T sub A, then either T sub A indicates a termination due to stack overflow, or an execution of C exhibits UB, or there exists a trace T sub C such that C executes with T sub C and T sub C is identical to T sub A. We return to our example. Look at the procedure call in assembly. First, we see that the arguments of scanf are explicit in the IR call instruction but implicit in the assembly. Figuring out the arguments to a procedure call in assembly can thus be tricky in general. Next, we see that scanf is passed a stack address of X as argument in assembly. As an external call usage, scanf may potentially observe or mutate the part of memory accessible to it. We want to encode that it can only access the part of stack that corresponds to X and not the entire call stack of Radiant. This is a calling convention requirement that must be ensured by the assembly procedure. A possible solution to this is use of complex invariants over the behavior of callee. We propose an alternate solution. Our solution is distinct identification of allocated locus in assembly. We identify the region in stack that corresponds to a local and mark it distinctly. This is enabled through annotations in the assembly procedure. We add annotations for allocation, deallocation, and procedure call events. For allocation and deallocation, we define new alloc_s and dealloc_s instructions. For procedure call, we add annotations to the assembly call instruction. An annotation for local allocation is identified through a new allocation on stack indicating alloc_s instruction, which takes 4 arguments: address, size, required alignment, and identifier of the local. Alloc_s identifies the region of size starting at header as belonging to the local. For an execution of alloc_s to be error-free, it must satisfy well-formedness constraints which require the region to belong to stack previously and not some other currently allocated local, and the address to be aligned by requested alignment. Notice that these well-formedness constraints are similar to well-formedness conditions for an alloc instruction in the IR program. We impose a soundness requirement on the alloc_s instruction such that only an annotation that corresponds to an allocation in C is allowed. This is enforced by writing both alloc_s instruction in A and alloc instruction in C to produce observable events. Recall that our refinement definition requires identical sequences of observables to be produced in both procedures. With the new annotation instructions, we define refinement from C to A through existence of an annotated A such that annotated A refines C. Thus, our refinement is through existence of an annotation. This refinement definition is general enough to support a wide range of transformations. For instance, it supports merging of multiple allocations where a single stack pointer decrement is used for allocating multiple locals. A more noteworthy capability is support for dynamic allocations and deallocations, a capability which is missing in the ComCert certified compiler that notably only supports pre-allocation. Supporting dynamic allocations enable us to support C99 variable length arrays. On the other hand, the observation of allocation and deallocation precludes certain transformations. A fundamental limitation of the definition is that relative order of allocations, deallocations, and procedure calls must be preserved from C to A. A class of transformations that may not respect this constraint are those that reuse stack space. We argue that such transformations are relatively rare. Our proof method, which realizes this refinement definition, is a determinized product graph. A product graph is a cross product of the control flow graphs or CFGs of the two procedures C and annotated A. In prior work, product graph was used for encoding lockstep correlation of paths. We extend this to lockstep correlation of allocation, deallocation, and procedure call events. Our determinized product graph X is a 4-tuple of nodes, edges, a deterministic choice map, and node invariants. A product graph node is a pair of C and annotated A nodes. A product graph edge is a lockstep execution of a path in A followed by a path in C. The deterministic choice map determinizes the non-determinism in C using choices in A. A non-deterministic address returned by a lock instruction in C is determinized by a stack address, and the non-deterministic memory contents are determinized to stack memory contents. The node invariants in X associate a first-order logic predicate with each node. To witness refinement, a determinized product graph must satisfy 11 soundness requirements. These requirements are categorized into 7 structural requirements, which dictate the structure of the product graph, and 4 semantic requirements, which require discharge of proof obligations. We identified 2 additional requirements that enable a faster SMT encoding and correlation of search space optimizations. Our algorithm for automatic construction of a determinized product graph is modeled as a such problem. We construct the product graph X and annotate A incrementally. Our algorithm supports 2 modes for annotations. In black box mode, the annotations are guessed through a restricted grammar. In white box mode, the annotations are passed as external untrusted hints to the algorithm. The sources for these hints include lightly instrumented compilers and debug headers, among others. In both cases, the annotations are validated before use. Our algorithm for inferring node invariants is a counterexample guided guess and check procedure. The candidate invariants are guessed through a grammar which includes affine inequality relations over variables, registers, and stacks nodes, memory region contents, and addresses equality, and custom invariant shapes for showing separation of regions in stack. The proof obligations generated for the semantic requirements are represented as first-order logic predicate over bit vectors, arrays, and uninterpreted functions. We provide 3 different encodings for an allocation state query. The full array encoding is a naive encoding which uses SMT arrays. The partial interval encoding is an improvement over full array encoding which encodes certain relations using bit vector comparisons instead of arrays. The full interval encoding is an optimized encoding which uses only bit vector comparisons but can only be used if certain constructs are not present in the input procedures. The algorithm is implemented in a tool and we evaluate it using a set of experiments. In the first experiment, we assess the capability to handle diverse local allocation patterns using a set of micro benchmarks. We also evaluate the performance of the 3 SMT encodings as part of this experiment. In the second experiment, we attempt to quantify the cost of annotations. In the third experiment, we evaluate the tool on a real-world program. We run 3 SMT solvers in parallel for a maximum of 10 minutes for discharging a proof obligation. We use a timeout of 8 hours for each procedure level refinement check. In our compilations, we disable interprocedural transformations through compiler flags. Finally, to simplify proof effort, we use mem2reg on the unoptimized IR, which promotes non-address taken local scalars to registers but retains address taken locals and arrays. In the first experiment, we use 18 micro benchmarks, which contain various programming patterns for local allocations. We use 3 compilers at O3 optimization level for compiling these programs. We use 3 SMT encodings auto, which can use full interval encoding if applicable, forced partial interval encoding, and forced full array encoding. Of the 54 refinement checks, our tool is able to successfully validate 45 compilations, representing a success rate of 83.3%. The full interval encoding is found to be 1.7 to 2.2 times faster than partial interval encoding and 3.5 to 4.9 times faster than naive full array encoding. Our failures are due to invariant inference limitations, black box annotation restrictions, and SMT solver timeouts. For our second experiment, we create 2 versions of the same benchmark suite. In the first locals version, we use global arrays. In the second locals version, we use local arrays. The 23 procedures selected for this remain otherwise identical. We compile using Clang at O3 with a vectorization which compiles the loop identically in both versions. We pass an unroll factor of 64 for tackling the unrolling and vectorization. Like previous experiment, we run the locals version on a first partial interval encoding as well. We find that the annotation and invariant inference in the locals version results in a significant overhead where the globals version is 2.5 times faster than the locals version. The full interval encoding is found to be 1.9 times faster than partial interval encoding. In our third experiment, we compile the Bezier-2 procedure from Spec 2000 using Clang at 3 optimization levels, O1, O2 and a custom O1 minus where we disable certain optimizations. A binary compiled using O1 minus is 2% slower than O1. However, this is still 5% faster than the binary compiled using the ComCert certified compiler. With O1 minus compilation, our tool is able to successfully validate 64 procedure pairs. The remaining 8 procedures are all with greater than 190 assembly instructions. Our largest proof takes about an hour, and on average, each proof application is discharged in less than a second. To summarize, we provide a formal execution semantics for the purpose of translation validation of an unoptimized IR of a C program and its compiled 32-bit x86 assembly in the presence of dynamically allocated local memory. A refinement definition for correct translation in this context, an algorithm for converting the correct translation task to first-order logic assembly queries, and a prototype implementation and its evaluation. This concludes my talk. Thank you for listening.